Yeah. Comes on everyone. Let's start off. The last thing that we did, we started with the rigid body constraints. Let's go ahead with one more problem. We got two perpendicular walls here, and there is a rod. This is point A, and this is point B. So A is pulled with constant speed u. This is theta. L is the length of the rod. C is the center. D is some random point here at a distance of D from A. There. So there is a lot of things there. So one side of the rod is sliding on the wall and the other is sliding on the floor. And then what you did, you started pulling this point A, the one on the floor, with a constant speed u. Find velocity of B, acceleration of B, velocity of point C at this instant. Find the trajectory of point D. Trajectory meaning in which path does point D travel. So options would be something like straight line, circle, and all that stuff. So let's get this. Everyone should give it a try. Others do keep your cams on. Anyone not clear with the question, please ask me. I'll explain again. So we got a rod. The B is on the wall and A is on the floor. And when you pull it A, this is how the picture will become, everyone. Next moment, the picture will be like this. And then it will be like this. Can you see how the rod is moving? So the rod is sliding down there. So find the velocity of B, velocity of C, acceleration of B at this instant, and the trajectory of D. What path does D take? This will be a good more than one choice question at your level. Yeah, the speed is fine. Get me the acceleration part. Karthik, that looks wrong. Yukti, that looks right. Right, right. I'll give a minute more and then I'll show you. Get me the velocity of B, C, and acceleration of B. Hmm. There are a lot of things there. Let's see the velocity part. That's the easy one. So if you got a rod, it's a rigid rod. So velocity along the rod must be same. So this point A is going this way. This be VA. B is touching the wall, so it has to go down. This is VB. So this angle is theta. This angle is theta. So the component along the rod will be VA cos theta. This will be 90 minus theta. So this component will be VB cos 90 minus theta. Cos 90 minus theta is sin theta. In a rigid body, the velocity along the rod must be same. So VA cos theta is VB sin theta. So VB is equal to U cot theta. I already showed it down. So there. Got the velocity part? Next thing. How do you find for the acceleration? So acceleration of AB will be dVB by dt. U is constant, but you have to differentiate cot theta now because theta is a variable. And cot ka differential is, you can get it from differentiation also. You can take x, y and differentiate. It works. Cot ka differential will be minus cosecant square theta d theta by dt. So cot theta, right? You have differentiating with time. So theta is also a variable. It's a chain rule. Now, how do you get d theta by dt? If you remember, this problem has a lot of similarities with this guy. Question number 6. Tasks, the d theta by dt and all that stuff. So it has something similar to that. This was x and this was u. And this was theta and this is length L. So x is equal to L cos theta. When you differentiate on both sides, dx by dt will be L. This will be minus sine theta d theta by dt. And dx by dt is nothing but VA. So minus VA by L sine theta is d theta by dt. You can take this and substitute in this. That will give you acceleration of B is equal to minus U. Cosecant square theta is anyway sine square theta. VA is also U by L sine theta. U square by L sine cube theta. That's your acceleration of B, everyone. If your theta changes, you have to get the velocity and differentiate. There's no way out. This and the sixth problem are kind of have some similarities. Clear with this? Remember, only velocity is valid. The power method is valid for velocities. Velocities along the rod must be same. It's always for the velocities. Acceleration sometimes, yeah, it works out if theta is constant. If theta is constant, then acceleration also will work. But here theta is changing, so that creates a problem. Next thing. Still, the question is not over. What about velocity of the center? Just give me a minute. Um, बिल्कुल, आगे नंबर है। Yeah. How do we do for the center? If you look at the center, think of like this. So this coordinate will be x comma 0. This coordinate will be 0 comma y. This guy is going down vb. This guy is going this way va. So dx by dt, x is increasing, so plus va. dy by dt, y is decreasing, so minus vb. So that's the meaning of going downward. So if you look at the center coordinates, that would be x by 2 comma y by 2. So therefore, position vector of C is x by 2 I cap plus y by 2 j cap. Then velocity of C will be half dx by dt I cap, half dy by dt j cap. And dx by dt is va by 2. And this is minus vb by 2. U by 2 I cap minus u by 2 cot theta j cap. That is your velocity of the center. It's not going in a straight line. It is going in some. Actually, you can find the trajectory of C also. If you look at the coordinates of C, x coordinate of C square plus y coordinate of C square will come out to be L square by 4. This is actually equation of a circle. Means if you actually try to draw the path of this thing, this would be the center, origin. This would be the radius, and it is going in a circle like this. The center of the rod is going in a circle. Did I tell you right? The general equation of a circle. Did I show you a general equation of a circle like x minus h whole square plus y minus k whole square is equal to r square. H and k is the center. R is the radius. In this case, h and k are 0 and 0. This is the meaning of radius of trajectory, equation of trajectory. Now I'm asking you the trajectory for point D. So D is at a distance of small d from the point A. How does this point go? So A is going in a straight line, B is going in a straight line, C is going in a circle. How does D is going? Any doubts so far? Think for a minute. How do you get the trajectory for D? Let me help you out. Find the coordinates of D in terms of x and y. Let A ka coordinate be x comma 0 and B ka coordinate be y comma 0. Find the coordinates of point D. Start from there. That should give you some idea. Let's see the coordinates. It's all geometry there. If you see, we're just playing around with that coordinates and stuff. So this was there. This is let's say this is L, this is theta. Let me draw a little bigger. This is theta, this is L. Your point D is somewhere here. This distance is small d. So this distance will be d cos theta. This distance will be L cos theta. And this height will be d sine theta. So you're done. So x coordinate of d would be L minus d cos theta. The y coordinate of d would be d sine theta. Those are your coordinates. You can find the speed also. But if you do something here, if you do x by L minus d ka whole square plus y by d ka whole square, this would be cos square theta plus sine square theta is equal to 1. This is x square by L minus d whole square plus y square by d square is equal to 1. This is an equation of an ellipse. So what is an ellipse? So it's like this. It's like take a circle and just smash it at the top. So kind of becomes like this. This distance here is 2a. This is called as major axis because it is a bigger one. This is 2b. This is called minor axis. If a is equal to b, it becomes a circle. The general equation of an ellipse is x minus h whole square by a square plus y minus k whole square by b square is equal to 1. The center of the ellipse will be h comma k. If a becomes equal to b, you can see that becomes the equation of a circle. And for this ellipse, the area of an ellipse, this is another result which is useful, comes a lot, is given by pi into a into b. A and b are half of that major axis. So it's like 2a is like your diameter kind of thing. So this is some stuff you should know. That's a little bit about ellipse. This much you should have an idea. Maybe I'll put this in the next page. How do you draw an ellipse? Ellipse has a very beautiful property, like, you take two fixed points, let's say S1 and S2, right? Take a string tied to these points. Then what you do, take a pen or a pencil and make the string tight. So put it there and keep the string tight like this. Now try to draw a circle. Keeping the string tight, draw a circle. The shape you get is an ellipse. So in a circle, what you do, you keep one fixed point. How do you draw a circle? Take one fixed point, take a string, keep the string tight and draw, try to go around, you get a circle. In an ellipse, take two fixed points, put a loose string between them, then tighten the string by putting a pen or a pencil like this. So you're pushing it with the thing, and then keeping the string tight, try to make a circle. You get an ellipse. So you will learn this in max. So in ellipse, right, these points are called focus, F1 and F2. So there are two focuses. So the ellipse ka property is this. You take any random point on the ellipse, and if you join them, F1a plus F2a will be always equal to 2a. 2a is your major axis. And that's a small property of an ellipse. It has all very nice properties also. You'll see later on in ray optics. If you send a light ray passing through F1, it will always pass through F2. Meaning, if someone sends a light ray through F2, if this was a mirror, it will hit this mirror and then will bounce and will go through F2. So in Hyderabad, right, there is a palace. So what they did, the queen and the king ka chamber, right? The king where he goes in the court and everything. This is the place where the king ka court was built, and this is the place where queen ka chamber was built. So whenever the king talks, she can actually hear the sound directly. So after hitting the wall, it reflects and goes to the other cabin. So it was something designed like that. And also, I think in Europe, I don't remember the country, but there was an architect, right, who is also a politician. What this guy did, he constructed an ellipsoidal chamber where he kept the leader of the opposition leader, opposition ka jo bhi leader hai, he kept his chamber at one focus and he kept his chamber at another focus F2. So whenever they talk, you can actually hear what they're discussing. Anyway, so does work. That's a little bit about ellipse. So this point is going in an ellipse. Yeah, this is for when L is not equal to D by 2. D is not equal to L by 2. Or D is not equal to 0 or L. Because 0 and L will become A and B, then it will be a straight line. L by 2 will become a circle. Yeah, you can also say circle is also an ellipse, where A is equal to B. Acceleration part is this. All clear with this? That's a bit about an ellipse. Ellipse does come a lot, maybe 3-4 times. So it comes in thermodynamics. It does come at few places. So you should have that much idea. You don't need more than that in physics. Clear, na, Yukti? Next thing. There, that's a bit about constraints. So that's the first part in NLM, constraint motion. The second part is your free body diagrams and stuff. So before going to that, we have to define the Newton's laws of motions. So Newton's first law. So what is Newton's first law? A body continues to be in a state of rest or uniform motion until and unless force is acted upon it. Now, if you see, right, the statement tells you a few things. First thing, it talks about something called rest or uniform motion. Then it also talks about something called force. So how do you know, first of all, something is at rest or something is moving? If you remember in kinematics, we discussed this inertial and non-inertial frame. Remember? So when you say something is moving or not moving, the important thing is first you define your frame of reference. So the first law gives us the idea, the concept of force and inertial frame. So it talks something about something called force, which is required to change the state. So first law gives us the concept of inertial frame. What is an inertial frame? Any reference frame which you have chosen for observation. What is a non-inertial frame? Any frame that is accelerating with respect to inertial frame. This is any frame of observation. Now, when you think about these forces in nature, right, we have only 4 types of forces. Every force that you can think of can be classified into 4 fundamental forces. There are 4 types of forces. The first thing is your gravitational force. This force, right, is due to the interaction between masses. This force comes whenever masses are involved. And this force, right, is the range is infinity. What is range? Again, not projectile ka range. Range means up to what distance you can reach. For example, uh, I can hit you with my hand at a distance of maybe 1 meter. But if I have a stone, I can hit you even at a distance of 10 meters. So having a stone, I have more range. I can interact with you at a much larger distance. So a gravitational force has an infinite range. So gravity can act for really long distances. The strength is weak. It's a weak force. The magnitude is weak. The second thing is electromagnetic forces. This comes due to the interaction between charges. These ranges is in meters. This is a very strong force. Think about it. When you're holding something, what force actually are you exerting on that body? When you're holding a pen or you're lifting a block, you know what you're doing? The molecules on your hand are repelling the molecules on the other body, right? There is a nuclear repulsion between the molecules. When you're sitting on the chair right now, the molecules, right, on your seat are repelling the molecules on you. And that nuclear repulsion is what is you feeling like I'm sitting on a chair. So what you're actually experiencing is an electromagnetic force. It's an electric repulsion at a fundamental level, right? And now think about it. So when you take a pen and lift it, just think about it. Huh? The whole earth is attracting that pen, and you, with a single hand, have lifted it, isn't it? That means the whole earth is on one side pulling the pen down, and you on the other side, with a single hand, you lifted the pen. That's what I mean by the force is strong. The force between your hand and the pen is stronger than the force between the pen and the earth. So roughly, if you look at the ratio, right, if this is 1, this guy would be 10 power 36. That's the kind of numbers we are looking at. It's huge. The third thing is nuclear force. This we will not deal with this. This is the interaction between nucleons. Nucleons or neutrons and protons. This is inside the nucleus. This you will never encounter in real life. Like you do get them in nuclear bombs and nuclear fusion reactors, but you don't get to see them daily on the road until unless Trump starts throwing nuclear bombs at everyone. So that's a different thing. So nucleons are neutrons and protons. The reason you don't see them is because this is very small. We are talking in the distance of 10 power minus 15 meters. This is called 1 Fermi. That's very small. Your molecule ka size is what? 10 power minus 10, 1 angstrom. But these forces are very strong. We are looking at an order of 10 power 38. Meaning if gravitation is 1, then strong forces are 10 power 36, and these forces are 10 power 38. Just to give an example, when you're in school, right, you studied this. Our school teacher told us this, like charges repel, unlike charges attract, right? And the same teacher also said, maybe chemistry teacher, right? Inside a sodium atom, there are 11 protons sitting inside a nucleus. If there are 11 protons sitting inside a nucleus very close to each other, and if protons all are like charge, shouldn't they repel and fly off? If 11 protons, which are positive charged, are sitting inside a nucleus of a sodium, which is very small, shouldn't they just repel and fly off? But they don't. That is where people got a doubt. That means there is someone else who is inside who is keeping them together. That's your nuclear force. So you don't see them until unless the distances are very small. The fourth one are weak forces. This is all that, dark matter, dark energy, all that stuff. We have no idea what is this. We have no idea what is this. So this is all that unknown. This is still being researched. So primarily, we will be focusing only on A and B in our portion. C also will not touch it. But there, every force that you can think of can be classified under these four forces. The spring force, normal reaction, friction. Yeah, you can think of anything. They all get classified into these four. But mostly it is A or B. B actually most of the time. Anyway, so that's a little about the forces. Now in mechanics, we deal with normal reaction. We will simply call it normal. Tension forces, that is the full name actually. We'll simply call it tension. Spring forces and friction. These are the four forces we deal in this thing. In our chapter, we will deal with normal reaction and tension and spring. Friction has a separate chapter for itself, right? We will, yeah, corks and gluons will not get into that, right? So first we will do normal and tension. Spring we will do end of the chapter, and friction is the next chapter. So first of all, what is a normal reaction? So if you are comfortable with these four, yeah, then I think we have all the ingredients ready. Normal reaction symbol is N. When two surfaces are in contact, the nucleus of the molecules repel each other, generating a force along the common normal. And you already know what is a common normal. Last class we discussed. That means if you can actually zoom in and if you see this at a molecular level, the nucleus are a bunch of positive charges and you're pushing them towards each other. So a normal reaction is nothing but an electromagnetic force. So when you're sitting on the chair which you're feeling is actual electromagnetic repulsion. So if you look at the molecules here, so this molecule is repelling like this molecule is repelling, this molecule is repelling, this is repelling. So it's not one, a lot of molecules are repelling here. Because of this, we can see there's almost a kind of a symmetry there. So this molecule repels, this molecule repels, this is repelling, and this is repelling, and this. So in reality, when you say you're touching each other, you're actually touching at very few points. So that's what is happening. That means if you go and punch your brother, and you can tell him, see, you're not actually touching them. It's a very high repulsion. So you can go and punch your brother and say, see, I didn't touch you. It's an electromagnetic force. And then he'll punch you back and say, see, I also didn't touch you. It's also an electromagnetic force. So kind of doesn't work. But you're not actually touching anything. Right now, the table which you feel you're touching, you're not touching. Because if you actually touch, both the nucleuses will fuse because of nuclear fusion, and there'll be a blast. Your whole building will go off. So in reality, you're not touching anything, and you should be happy that you're not touching anything. So this is how the normal reaction will act. So currently, right, in France, they're making ITER. Yeah, if you ever heard about it, it is an international, 23 countries are building the world's first nuclear fusion reactor at a large scale. In that, you take hydrogen atoms, you combine them to form helium. Basically, you're creating a sun on Earth. It requires a temperature of 10 lakh degrees. That's the big problem there. These are all common normals. So that means whenever you have two bodies touching here, the forces will be along these common normals. Clear with this? This is your normal reaction. The next thing, tension. This also we talked about a bit. So technically, right, when you say tension, it is not a force. It is a state of the material. The body is under tension. Somewhere down the line, people started calling it tension. For example, see, you're angry. You being angry is the state. When you're angry, you start shouting on everyone. So that is your, way of releasing that anger. The same way, the body is under tension. Because of that, there will be a force generated. That is called tension force. But people simply say tension. But yeah, if you go by English, tension is not actually a force. It is a state of the material. When a body is deformed, that is, the body is elongated or compressed. The body generates internal restoring forces. Look at the word internal, meaning these forces are inside the body, restoring, they're trying to bring you back to the normal state. So when you deform a body, the body is not happy with it. It's trying to push you back and come back to the normal state. These forces are what is called as tension forces. So be careful. Tension is not the external force. Tension is the force generated in the body when it is getting deformed. The molecules get distorted and they start fighting back to come back to the natural state. So these tension forces, which will try to restore the body to the natural state. They try. We have a full chapter on this later on called elasticity. There we will see in little more detail, but that is the tension there, which try to restore the body to its natural length. Let's say you're sitting in your class and three people can sit on the bench. If a fourth person tries to come and sit there, what happens? You feel really, uncomfortable. You really don't feel good about it. Then you start pushing and then you start shouting, fighting, all that is your internal restoring forces. You want to get back to three people on the bench. So same way, the molecules are distorted. They do not happy about it. They start fighting back. If we say the body is under tension. So tension is a state of the material. The body is under tension and the force generated are tension forces. But anyway, so when I say tension or use in the book tension, they're talking about tension forces. So basically tension is due to the deformation of the bond structure. So fundamentally, if you go inside, you will see the bonds are getting deformed. This is also electromagnetic force. And we know strings and this thing, rods and strings. What is the difference between a rod and a string? They can pull and push. So a rod can pull and a rod can also push. For example, if you take a rod and you put a block. So what does the rod do? The rod pulls. The weight is trying to pull the block down and the rod will get under tension. It'll try to pull you up. The same thing, if I do it in the reverse, if I keep the rod down, the weight is acting down, the rod will also push up. Simple things. So rods can push and the rods can pull. But if you take a string, they can only pull, they can never push. That is how their structure is. They're okay under tension, but the moment you try to compress them, they just go off. Look at your mobile ka charging cable. If you try to pull, it will come, but if you try to push, it will just become loose. They can only pull. So in certain questions, this will create a problem. Tension, mg. String pulls. But if you put something like this, the block will just fall down and the string becomes loose. Tension becomes zero. Clear with this? There, that's your Newton's first law. Regarding spring, we will talk about that in the end. Friction, we have a separate chapter. But these are the two forces we'll deal with, normal and tension. All clear so far? Next thing, Newton's second law. Before jumping into that, we need to define something called momentum. Now, this is one more thing in physics. Always, remember the definition, that is good, but also remember what it means. For example, if I ask you, what is momentum? What is momentum? What do you guys think? What is momentum? Mass into velocity. Great. What does it even mean? Did you see the problem there? You are good with the definition, but you don't actually know what it even means. So for everything, right, there'll be two definitions, a proper technical definition and a definition for yourself to understand. It's okay. It might not be a proper definition. It could be an example. It could be a scenario or something, right? But you should be able to inherently understand यार momentum होता क्या है मतलब. So if you ask me what is momentum, this is what I think. Let me give you an example. Let's say if something is going with a speed of 1 centimeter per second, can you stop it? If something has a mass of 1 gram, can you stop it? So if a local train is going with 1 centimeter per second, you'll go and stand in front of it. If a bullet of 1 gram is going with 1 kilometer per second, you'll go and catch the bullet. What happened? 10 seconds before, you're pretty confident. When I said 1 centimeter per second, you're not scared of the speed. You got scared of the mass of the train. When I said 1 gram, you didn't get scared of the mass of the bullet. You got scared of the speed of the bullet. Isn't it? So what you're actually getting scared is not the mass, not the velocity, but the product. So what is momentum? This is what I think. Higher the momentum, the more difficult to stop the body. Now I understand. Oh, momentum matlab ye hota hai. So next time when someone asks this question, can you stop this body? It's not the mass, it's not the velocity. What you are interested in is the momentum. Is the body has more momentum or less momentum? So if you see only mass or velocity, it can be misleading. It's more difficult to stop the body. This is what I was saying. You should have a definition for yourself. It might not be a proper technical definition, but yeah, your brain can understand what you're talking about. That's a very important thing in physics, right? You should have your own understanding. You should have your own theories. You should have your own concepts. They can be little hazy and weird, but that's okay. That is a fun part of learning anything. If you just stick to the book without really understanding, and then go on. Photon, the concept is different again. So they don't have mass, but these formulas are not valid. So kinetic energy is given by half mv square, multiply and divide by mass. This thing I taught you in errors. So this can be written as p square by 2m. So you can also write momentum is root over 2 times mass into kinetic energy. And this thing depends on the frame of reference. So if a body is going with velocity v, if a person is standing here at rest, and if a person is going with speed v, this guy will say momentum is m into u. This guy will say momentum is m into u minus v. So depending on who is seeing it, the momentum will change. The momentum depends on your frame of reference. This is the momentum as seen by A, this is the momentum as seen by B. All clear with this? So that's your momentum. Then comes your Newton's second law. The force acting on a body is proportional to the rate of change of momentum. We have some really good problems on this, but we have a separate chapter for this called momentum, collisions, and all that stuff. I will do a little basics here. So F is proportional to dp by dt. So remember this thing. Someone asks you what is Newton's second law, don't say F is equal to ma. That's a blunder. F is dp by dt, proportional to dp by dt. F is equal to k into dp by dt. K is the proportionality constant. If you take SI units, what are SI units? Kg meter per second. This K ka value becomes 1. That means if you don't take SI units, if you take CGS units, K will not be 1. Then it becomes F is equal to dp bar by dt. But what is P bar? Mass into velocity. Then we have our product rule. So force is equal to m into dv bar by dt plus v bar into dm by dt. This is the actual equation. So again, remember, someone asks you what is Newton's second law, you will say F is proportional to dp by dt. That's it. If mass of the body is constant, then your term dm by dt becomes 0. Then your equation becomes F is equal to m dv by dt. And we know dv by dt is acceleration. From there, we get your F is equal to ma. So this F is equal to ma is a special case where mass is constant. So later on, we have a full subtopic called variable mass system. What happens if the mass of the system is changed? So if someone says F is equal to ma is Newton's second law, that's a big blunder. So yeah, keep that in mind. Clear with this? So this can be also written as, so F bar is equal to dp by dt. So delta P bar is integral F bar dt. This is your change in momentum. There's also a name for this. It is called impulse. That means if you draw a force versus time graph, I showed you this in kinematics. The area under the curve, this is the positive area, this is the negative area. So area under FT curve gives you change in momentum. Clear with this? Now, let me show you an example. Let's say we have a trolley. The railway ka compartment hota hai na, it's a trolley. It started raining. And because of this, the rainwater is getting collected at a rate of 10 kgs per second. So every second, 10 kgs of rainwater is getting collected. This trolley is going with a speed of u is equal to 5 meter per second. Let's say this is constant. And someone is applying a force F on the trolley. Mass of the trolley is 100 kgs. So straightforward question. Find the F external to maintain the speed. So how much force should act on the body so that the speed of the trolley is maintained? Did you ever do this thing? You're going on a cycle, your friend comes and jumps on the back seat. Your cycle slows down. You have to pedal more. Now, this is what people do. Huh? They will say, since V is constant, acceleration is zero. And since F is equal to ma, therefore F is equal to zero. This is a blunder. Why it is a blunder? Is the mass of the trolley constant? Mass is changing. So how can you use F is equal to ma? That's the problem. So what should you use then? F is equal to m dv by dt plus v dm by dt. Speed is constant, so this term is zero. So what is dm by dt? This is the rate of change of mass. Every second, by what amount is the mass changing? So this comes out to be, and this term would be zero. F is equal to v dm by dt. V is 5 and dm by dt is 10, 50 newtons. So even though the speed is not increasing, right? In order to maintain that speed, because as the mass is adding up, the body actually slows down. You have to apply this much force just to maintain the speed. Is this all clear, everyone? I'll give you one small one on this. Now you guys try. So let's say we got a trolley here. Rain is falling into the trolley. Rainwater is collected at a rate of lambda kgs per second. That is the symbol for lambda. And someone is applying a force. F is equal to F naught into T. It's not a constant force. You're applying a force which is changing with time. Mass of the trolley is capital M. Initially, the system is at rest. So you have a trolley whose mass is increasing. You're also applying a variable force. And look at the force. It is increasing with time. T is 0, there is no force. T is equal to 10 seconds, there's a 10 of naught force, and so on. Find the velocity of the trolley at time t. If the mass had been constant, you could have said F is equal to ma, then you could have used V is equal to U plus AT and you would have done. Here the force is changing, mass is changing. Let's get this. How do we handle this? We can go the long way, we can go the easy way. I'll show you both. If you go with this equation, F is equal to m dv by dt, after time t, what will be the mass? Your mass will be m plus lambda into t, because in time t, lambda into t amount of rain has fallen into the trolley. Now, when you apply the equation, F is equal to m dv by dt plus v dm by dt, this would be F naught t, that m will be m plus lambda t. This would be dv by dt plus v, I don't know, and dm by dt is lambda. And this would be a mess, like integrating and all. There is a better way. I think this will not work. You will actually get a differential equation which we can't solve. The easier version is this. I know delta p bar is integral f dt. What is this thing? This is m final, v final, that is a change in momentum, minus m initial, v initial is equal to, this will be f naught t dt from 0 to t. What is the final mass? Mass of the trolley plus lambda t. Initial mass is m, but your initial speed is 0. This would be f naught t square by 2. Therefore, P naught final is equal to F naught T square by 2 into M plus lambda T. Better? So use F is dP by dt. Don't split it only. Since you just want velocity, don't even get that. Get the momentum, and then from there you can figure out the velocity part. Making sense? Easy one. This is how you handle it. You cannot use your kinematics and all that stuff. More on this we will see in a separate chapter called center of mass momentum and collisions. We will see more. Sand leaking, rocket propulsion, everything is based on this thing only. What if your mass changes? But yeah, that's one problem there. The next thing, Newton's third law. What is Newton's third law? Yeah, for every reaction, there is an equal and opposite. For every action, there's an equal and opposite reaction. That's a one big bullshit definition. Tell me one thing. If I punch you, right? What do you mean by action reaction? Think of like this. Now, if I punch you, right, you get angry, then you go and bring 10 people to beat me. So the action is me beating you, and the reaction is you are bringing people to beat me back. So action reaction is I do something, and because of that, you're doing something else. But imagine if I punch you, tell me one thing, like, if let's say you're hitting me, did you touch me first or did I touch you first? If you slap your brother, right? Your brother will say, Mummy, dekho na, sister slapped me. But you also can complain, right? Mummy, dekho na, brother ka cheek has hit my hand. Both of them occur at the same time. So who is action and who is reaction? You're getting it? So the problem, the word, right? Action, reaction, it rhymes and it sounds well, but we have that the definition has a problem. So how do we define them? Yeah, but it looks good, but action reaction doesn't make sense. When you say action reaction, it is because I did something and because of that you did something. When you're touching something at the same time, that is also touching you. So there is no delay between them. So when two bodies interact, so this is how we can define this. The force between them. It should be equal in magnitude. Opposite in direction. Along the same line. They should be on the same line. At same time, there is no delay between them. Imagine there is a delay between. So whenever you walk on a floor, you know what will happen? Your leg will go inside, then you'll be pushed out. Your leg will be going inside, that will be pushed out. So it will be like you're jumping on a trampoline. There is a delay. So in real life, there's no delay there. They act on two different bodies. They should be of same nature. It has to follow the six conditions. What do you mean by same nature? Gravitation, electromagnetism, like that. So you have to satisfy these six conditions, and then you say it is a Newton's third law. Action reaction is a bullshit definition. But how do we work this out? So let me ask you a question only on this thing. So if you take a block of mass m and if you keep it on a ground floor, it is at rest. So my question here is, are mg and the normal reaction n, I know we will say action reaction pair. Meaning the word still sounds good, so we'll just use it. But remember, it doesn't make sense. What do you guys think? So when you draw this body, N and Mg, are they an action reaction pair? If you think no, then who are the action reaction pair then? So the important thing is this: forces will always come in pairs. You can't have a single force jumping around. So look at the problem with this. Most people think, they're action reaction pair. If you look at the forces, this is Mg, right? And this is N. They will say, sorry, it is at rest, so N is equal to Mg. Okay, first is satisfied. They're opposite, satisfied. Same line, satisfied. Same time, kind of. Act on two different bodies. Here, N and Mg both are acting on the same body. They're of different nature. Mg is gravitation. N is electromagnetic. How can a gravitational force create an electromagnetic, pair? N and Mg are not a pair, right? So N and Mg are not a pair. Then where are the pair of forces then? If these are not a pair, then the pair should come somewhere. The pair actually comes here. So if you take the block M, this thing you placed it on the earth, the mg on the block is coming because of the earth. So the block is being pulled down by mg, the earth is also being pulled up by mg. There is an attraction between the earth and this thing. So this mg is the gravitational force on block due to earth. These two are a pair. Now see, they're on two different bodies and they're of same nature. What is this mg then? This is the gravitational force on earth due to block. And the reason it doesn't move because earth is so heavy and the force is so small, almost negligible. But it is there. These two are an action reaction pair. What about the normal reaction? There is one force which is pushing this surface, there is one force which is pushing the floor. So when you're standing on a floor, the N is pushing your up and you're pushing the floor down. So these two are one pair. This is the normal between floor and the block. And the other two are a pair. So remember this thing, forces will always come in pairs. You will not find a single force hanging around. All clear with this? That's your Newton's first law, second law, and third law. Yeah, that's a bit of a theory there. The next thing, free body diagram or FBD. Very important thing. comes everywhere. Mechanics, electromagnetism. If you don't know how to do an FBD, it's very difficult to learn mechanics. Difficult, kya? You won't learn mechanics. So what is an FBD? It is a pictorial representation. It's not difficult, but it is important. It's a pictorial representation of forces acting on the body. That's it. Matlab, if there are 5 forces acting on the body, if you can show all of them on a picture, you're done. Okay, we'll talk about this after the break. Take a break, come back by 9:45. We'll continue from here. Any doubt so far? Chalo, come back by 9:45. Let's see, everyone. So this is a representation of forces acting on the body. So be careful. We should not draw the forces given by the body. Cams on, everyone. For example, you're sitting, right? If I ask you to draw your FBD, so what all forces will you draw? The chair you're sitting, the chair is pushing you up. You are pushing the chair down. We will not draw that. We will draw the chair is pushing you up. Your hands are lying on a table. The table is pushing your hands up. The earth is pulling you down. So all those things. So how to draw an FBD? Steps to draw an FBD. Others, comes on. First thing, choose your system. And draw the body with the same orientation. This is one thing. I see people doing it. They draw the whole body as a point. It is not wrong, but later on you'll have a lot of problems with this when we do rotational mechanics. You, so draw the body with same orientation. Meaning, suppose let's say we have an incline and we have a block like this. So if you're going to draw them, let's say this is A and this is B. So you draw it the same way. If A is this way, draw A also that way only. Don't put a point. In some books you will see this, and they'll write A as a point and then they'll try to draw the forces. Don't do that. Draw the full body. B is at an angle, so draw B also the same way. Don't draw B like this horizontally. Keep it in the same way. It matters a lot. Maybe not in NLM, but later on it will matter. So better to be careful from now. Second thing, draw the weight vector mg downward. Third, for every point in contact, draw a normal reaction. With appropriate symbols. For example, let's say we have a body like this. If you see here, you're touching here, you're touching here, and you're touching here. You're touching at 3 points. So when you draw the normal reaction, you draw them N1, N2, N3. They're the normals, so towards the center. For every string and a spring, draw a spring force or a tension force. If there are 2 springs and 3 strings, then you put 2 spring forces and 3 tension forces. Or rods. Draw tension and spring forces. Then, so this is important. Instead of remembering stuff, you can remember the process. So I'll give you some shapes. You just have to draw an FBD. I know some of you are comfortable, but let's do it. I'll give you one example. So I'll start with a simple one. Let's say we have two blocks, M1, M2. Now, if I ask you to draw the FBD of these blocks, M1, M2. So one easy way to think, right? Whenever I say draw an FBD, think it is you. Think you are M1. So think of, M1 is your little brother sitting in your lap. So what are the forces acting on M1? Your own weight, M1G, and M2 is pushing you up. That is your N1, right? If someone is sitting on your lap, you're going to push them out. What happens to M2 then? If you're going and sitting on someone, what you do? You push them down with N1. Remember this thing. It is not M1G. M2 does not know who is M1G. Are you getting it? The force between M1 and M2 is coming because of the nuclear repulsion, the molecule repulsion between them. M2 does not know who is M1G. But you can say, sir, but because of M1 only N1 is coming. True. But when you draw an FBD, you always draw the direct forces. For example, if I take a book and hit you, who is hitting you? If I take a book and hit you, who is hitting you? Not me, it is the book. Yeah, I'm responsible, but I'm not hitting you. I didn't even touch you. It is the book which is hitting you. You're getting this? So because of M1G, you're getting a N1. That N1 is acting on M2G. So if you ask M2, what are the forces acting? It will say there is an N1, my own weight, and the normal reaction from the ground. Are you clear with this? You should not draw M1G on M2 because M2 does not know who is M1G. The only interaction between M1 and M2 is that repulsion between this surface, which is normal reaction. Are you clear with that? I hope that part was clear. Clear, na, Ananya? Ahana? Manav? Clear? Great. Now I'll give you a few shapes. You can just draw them. Again, don't think too much. Whatever you think you draw, when I show you, you can verify. That's the best way to learn. I just want the forces, okay? No need to resolve components and all that stuff. So there is an incline, there is a triangular wedge on top of it, and an M3 block on it. Just draw the FBD M1, M2, M3. Let's see. So step one, draw the body as it is. Don't change the size or don't change the shape. Then there is a normal from the ground. Then you have your own weight. And this is a force here, N2. So this triangular wedge. So the same N2 will act on this guy. You have your own weight, M2G, and M3 sitting on top of you that is pushing you down with N3. So remember, every body will have only one weight. This N3 is pushing you up and your own weight is pushing you down. That was easy. All clear with this? This is important. You should know how to draw the forces. That's it. This is the thing. FBDs and all. They should know how to draw the forces. Anyone confused with this, please ask. Great. I'll give you a few more. So let's draw them. Finish them off. Let's see. Normal from the ground. Your own weight m1g, n2, n2, n3, m2g. You can put anything, huh? N1, N2, N3. Yeah, the numbers are, the alphabets are fine. There. So they're pushing each other there. And what about this guy here? If you take this is tension T, this thing we saw in the string constraints, this will be 2T and this will be 2T. This is M2G, this is M3G, and this is M1G. All clear with this? Any doubts on this? Next one. Hmm. You know these pictures. Now listen to this thing. Huh? This is important. When you're drawing a wedge, this is one mistake generally happens. If you look at this pulley here, this pulley is fixed to the wedge with a rod or a support. So keep this in mind. Whenever you have to draw a wedge or anything, you have to include the pulley always, because you can't draw it separately there. The pulley is part of the system. Pulley is included with the wedge. You cannot separate it because there's a rod, and then you have to draw the forces due to the rod. That's the one common mistake that happens. People forget that. Now look at the forces. The string is pulling tension. The string is pulling tension. There. Now, if someone is asking you find the force on the pulley, it is a resultant of these two tensions. You'll get questions like that also. Find the force acting on the supporting rod of the pulley. So the force acting on this supporting rod is the resultant of these two tensions. Then you have one normal reaction here, N1. Then you have your own weight, M2G. Yeah, those are all the forces there. This is N1, this is M1G. I'm not resolving components for now. This would be 2T because there are two strings, and this is M3G. Please check your answers. I am drawing all of them. In case you're confused or not clear, please ask. If the string is set to have mass, yeah, if the string has mass, you have to count that also. That M also will get included. Look at this thing here. The pulley has to be included. People forget, people generally forget this pulley. So you get wrong answer. So that is tension. This is tension. This is tension. There are three tensions. This is one normal reaction. This is weight, and this is N2. This is N1, and this is M1G, and this is tension. So this will be 2T, this will be 2T, this will be this pulley, if you see, right, interestingly, this is T and this is T. So you have to draw both. This is N1, this is M1G, and this is a normal reaction N2. This is N2 and this is M2G. So you will have a tension at an angle here. That if you have a pulley attached to the wedge with a rod, you have to include the pulley. All clear with this? Yeah, that's some FBDs. You should be comfortable. You'll do problems, you'll get used to it. I'll also send you a small sheet in case you want to practice, you can do that. I'll send you maybe some 10, 12 questions on this. Great. So there, now you know constraints, you know FBDs. We have the main ingredients. Next thing, so before jumping into things moving, we will talk about equilibrium. So we have already done this a bit before in vectors, equilibrium, right? So I'll just bring it from there. If you remember, we did this thing in resolution of vectors. There. So exact same stuff. So how do we solve problems? Steps to solve. If you see, right, we always try to, formalize the steps. That helps a lot because in the exam, right, M2G sine theta, I'm not taking any components here, right? Just forces. There is one more tension here. You're right. Maybe I'm forgetting that. So the thing is, when you see a question and array, a question is ऐसे steps होगा, and if something changes in the question, you'll be able to understand, where you have to do the adjustment. So always try to formalize the process. You should have an idea roughly, at least, how do you even start a problem? So people say, I go to the exam, I blank out, or when you see completely new question, right, you won't get any ideas to approach because you should have a formal approach first of all, and from there you can deviate. If you don't have any proper process, then any process is random only. So choose a system, draw an FBD. How to draw an FBD? That also taught you the steps already. Second thing, assign accelerations. So this thing is like a general steps for everything. So assign accelerations to the bodies. So there are 3-4 bodies, assign A1, A2, A3, and find relation between them using constraints. Yeah, in the next class, we'll start moving things. Choose your X and Y axis and resolve your forces. And accelerations along them. Apply F is equal to ma bar along X and Y and solve for equations. If your system is in equilibrium, then A is 0. That's it. Those are the steps. All clear with the process? Great. Let's see a few questions. Then I'll go ahead to. If the system is in equilibrium, find the ratio of m by m. There, two questions. This is the smooth incline. Find the ratio of capital M by small m if the systems are at rest. Mhm. Try. I'll give you a minute more and then I'll show you both. Let's see the first one. Choose your system. So there are two blocks here. Start with tension somewhere. I'll start from here. Uh, let's call this thing T. This is mg. Now, since this block is in equilibrium, tension must be equal to capital Mg. Now, this is the same string. So this will be tension. This will be tension. This will be tension. So this will be 3T. If this is 3t, this is also 3t. If this is 3t, then it is pulling equally on both the sides. This will be 3t by 2 and 3t by 2. And this is your small mg. So small m is also in equilibrium. Therefore, 3t by 2 is equal to small mg. Then you're done. So take this and substitute here. You end up with capital M by small m is 2 is to 3. Make sense? It's all about getting tensions. If you see, we did the same thing in constraints, finding the tension ka ratios. Yeah. Get the next one also. This is important. The incline ka components. And incline ka components, we did it in projectile on an inclined motion. Remember? G sine theta, G cos alpha. I taught you there how to take components for an incline. So if you take the incline and this is your block, look at the forces. If this was your mg, this was theta. This is also theta. That is 90 minus theta. So if you resolve the components, this will be mg cos theta. This component will be mg sine theta. So if you take this block here, this was the tension. This was mg sine theta. This was mg cos theta. And this was your normal reaction. Since the block is at rest, tension must be balancing mg sine theta. So if this was tension, this will be tension. This is also the same string. This is also same string. This is small mg. So we have 3 times tension is equal to small mg. Just divide them. You end up with solve these two. Capital M by small m will be 1 by 3 sine theta. Clear with this? Easy. Let's see one more. Like these are all basic ones. Next class we'll do some good ones. We had a lot of theory today. I hope you remember this. We did something like this again in vectors. We have 3 identical spheres. So this is point 1, this is point 2, this is point 3, this is point 4, point 5, and point 6. All have same masses. M, M, and M. Find all normal reactions. The distance between the walls is 3r. All spheres have same mass and radius r. In vectors, we did with two balls, if you remember. Find all normal reaction system is at rest. Get a N1, N2, N3, N4, N5, N6. Remember, when I say choose your system, right, you need not choose only one ball. You can even choose two balls or all three balls. Your system is your choice. You can choose any number of however you want. Let's get this. Let's finish off. Last one for the day. Right, Sumana. Get the rest. Everyone should try. I'll give you 2 minutes and I'll 2, 3 minutes and I'll show you. We did have a discussion on this last time also in vectors. So there is one normal reaction you can see and tell the answer. Remember which one? N1. If you take all the three balls as one system, the only force which is balancing all three mgs is N1, isn't it? That's what I'm saying. You need not choose even one ball as a system. You can choose all three as one system. It would still work. Yeah. Keep going. Try. Whatever you can think of, do it. Like it's fine. Hmm. Let's see. First of all, did you guys get the angle? That is the important thing. If you don't get an angle, you can't go ahead. So if you join them center to center, that will be 2r. This distance is r. This distance is also r. So if you actually drop a thing, I didn't draw the picture properly, but this should have been a tangent to this guy. It should have been a tangent like this. So the picture is bad. It should be somewhere here. This should have been something like this. That should have been a tangent there. This also would have been r, and this angle would have been 60 degrees. In the same way, if I join center to center here, this angle also will be 60 degrees, and this angle also will be 60 degrees. Perfect. So let's call this thing A, B, and C. So draw the FBD of A. What are the forces? N6. Your own weight, mg. N5, making 60 degrees. N5 cos 60. N5 sin 60. You can clearly see n5 sine 60 is balancing the mg. Two mg by root 3. N6 is balancing n5 cos 60. That is mg by root 3. Perfect. Then I can take B, or I can take A, or I can take A and B actually. I can take B. Let's keep your life simple. This we saw in 5. This would be n4. This would be n3. This would be mg. Resolve them into components. This is n5 cos 60, n5 sin 60, n3 cos 60. Yeah, it's just a little long. N3 sin 60. Resolve them. N4 will be n5 cos 60, n3 cos 60, and n3 sin 60 is mg plus n5 sin 60. And we already know the n5 ka value, n5 sin 60 is mg only. This is 2 mg. From here we get n3 is 4 mg by root 3. Take this and substitute here. That will give you n4 and 5 mg by root 3 plus 2 mg by, that would be root 3 mg. I think I messed up. N4 is N5, N5 cos 60 is mg by root 3. N3 is 4, that's 2 mg. Is that right? 60 and 30. Weird. I could be wrong there. And 4, I'm not getting a feeling root 3 mg. What else went wrong? N5 cos 60 and 3 cos 60 is then 4. This is fine. Maybe right. I'm not sure. Then let's take A, B, and C together. And do check out N4. I don't know why. I'm getting very strong feeling it is wrong. Not sure why. This is N4, this is N6, and this is N2. We can clearly see N1 is 3 mg. N6 plus N2 is N4. From here I get N2. Shouldn't it be 2 root 3 mg? N3 sine 60, right? And then you're done. You'll get N2 from here. Substitute and you're done. All clear with the steps? Yeah. There, those are your forces there. So get the angles, draw the FBD. Yeah, this is a little long, but this is how you do. You can even take only C and do it. Works out. Any doubts on these things? All clear with this? So there we have done with free body diagrams today. So next class, we will have everything. We will also have things moving. We will see some good questions on tension and all that stuff, how to calculate tension and stuff. Okay, with that, we'll wrap up for the day. We'll catch up again on Monday. We'll continue from here. Do remember there's a test on Friday, so make sure to give it. I'll do send a sheet. Last time I forgot. I'll send you a sheet on the constraints also. Okay, with that, we'll wrap up for the day. So any doubts, anything else, please stay back and ask. I'll be free to leave. I'll see you again next Monday, same time. So take care, stay safe.